Have I answered your question so far, or the question I posed? How much data do you need? Probably not. I'll give you some context for answering the question. In the regulations, there are no direct requirements for you've got to bring in this much data this fast that I'm aware of, and I've read most of this stuff, and a lot of it many more times than once. There is, however, one area where data collection and the regulations are kind of brought together, and the data collection is implied, and that's in the area of leak detection. So, if you're a liquid pipeline operator, you fall under the PHMSA leak detection rules. If you're a gas operator, you don't, because they haven't been written yet. But PHMSA has said we intend to put some stuff out there once the technology catches up and we can do gas leak detection in a meaningful way. In fact, there's a whole new set of regulations that have come out since I originally wrote this paper about 6-8 months ago about rupture detection, right? So what's the distinction between rupture detection and leak detection? Yeah, I'm sorry, what'd you say? Catastrophic, right. So I'll contextualize it a little different way, it might be more helpful. So leak detection is I have corrosion and a small pinhole and I've got a leak and it's getting worse. That's leak detection. Rupture detection is Jim Bob's out there with a backhoe and just took the backhoe through the side of the pipeline. That's rupture, right? What we had in San Bruno was rupture. So the reality is, so there are new regulations out. There's a new standard out. It's API 1175, which is kind of a process safety standard. So a lot of the technologies how to do this are not well defined. But again, talking generically, in rupture, I want to know that right now so that I can start isolating that problem and shutting things down, right? One of the big problems in San Bruno, you know, the big gas leak and explosion that killed some people and burned a bunch of homes down, is it took them an hour and a half to get the gas isolated. So gas was flowing through a 24-inch rupture at full pressure, lit for an hour and a half. So it's basically a blowtorch going off in a big way in a neighborhood, right? So PHMSA said, we want a whole different standard for ruptures because we want those things discovered and dealt with quickly. So how would you find a rupture in dealing with data? Where would you find a rupture? Alan? Big change in pressure over a short period of time. That's typically the way you find ruptures. There's some other people that have other technologies that are ultrasonic and hydraulic, but the bottom line is if I see pressure move very quickly over a short period of time from high to low, that's a rupture, right? So in that case, I don't need a lot of data, but I need to see data changing really quickly. So that kind of seeing data change quickly actually works better in the remote telemetry devices than it does in the host, right? Because in the host, I'm bound by how quick I can capture that data, right? And then leak detection systems, they're all about what size leak can I find and how fast can I find it. And those are more about seeing normal operating condition and a deviation that I don't understand in a data-rich kind of way. All right, so let's talk about leak detection a bit more specifically. So API 1155, which has recently been replaced by 1130, but a lot of the criteria in 1155 are referenced in 1130. It says that when you're looking at leak detection systems and you're trying to pick an approach, you need to ask yourself questions about this. So one is sensitivity. Sensitivity is how small a leak can I find and how fast can I find it, right? So the reality of this is what most people do in leak detection is the way we start is we do a material balance. I measure, well, Russell, it's just a straight run pipe. It's 25 miles, it's 8 inches, I've got measurement on both ends. So I measure what goes in, I measure what comes out, and I alarm on the difference. So I'm moving 100,000 barrels a day through that pipe. With me so far? So what is if I get the most accurate Coriolis measurement for crude oil I can get, what percentage error would I expect to have? 0.1 if I'm really, really, really good. 0.5 is probably more reasonable, 0.25 to 0.5. So what is 0.1% of 100,000? It's 1,000. How big a leak is a 1,000-barrel leak? So I can't, doing simple mass balance, discover a fairly significant leak, right? So that's one of the problems with that. The other thing is, if my balance is out, I don't know where that leak is, right? So when you're looking at a leak detection scenario, you've got to address sensitivity. The second thing is reliability. So reliability is, of the leak alarms I get, how many of them are false alarms? So what happens if I give a control room false alarms? They go numb, they stop paying attention, they ignore them, they disregard them, right? So what happens is, if I get too many false alarms in a leak detection system, I'm going to ignore the one that matters. And there's documented evidence of that. In the Enbridge spill in the river up north was a good example of that. They were getting alarms, but they were ignoring the alarms. The other thing is accuracy. So accuracy would be accurately predicting where the leak is occurring, what's the flow rate through the leak, how much volume I've lost, and what type of fluid. So fluid tap matters in a multi-product pipeline, like a refined products pipeline where I'm moving diesel, kerosene, jet fuel, gasoline, etc. And then robustness. So robustness would be, yes, in the laboratory, I can find this leak exactly. Robustness would be, yes, but in the real world, can you find that leak in all these different operating cases? Right, so that's robustness. There's two basic kinds of leak detection. One would be an engineering model-based system, what's called a real-time transient model. What you do in those cases, I build a math model of the pipeline, and then I sample data, I feed it in, and it gives me an answer as to what you should see in pressures and flows and alarms on the difference. The other is a statistical model. And what it's doing is it's saying, well, given this range of pressures and flows, that looks like other scenarios I've seen in the past, right? So they have different levels of conformance to these criteria.